All right, gang, Matt, 6610. Kind of a chilly morning here in Kentucky as I'm putting up this video, posting this video. Well, I'm actually not posting it, I'm creating it. So I have my toboggan, well, actually my beanie. I found out the other day that if you get online and you want what I call a toboggan, if you actually, I want a Carhartt toboggan, right? You actually get a sled, so I guess it's called a beanie. All right, so put that in your trash can of useless information. All right, where are we? The last couple of videos, what we have done is we have got into the central limit theorem. And in general, sampling distributions. Now, what should you take away from that? What, in a nutshell, what should you be able to conclude? Well, I think first of all, when we studied the central limit theorem, I think there's two things actually. First of all, where we're headed, sorry, I know y'all have seen this ad nauseum, but in statistics, we spend a lot of time focusing on the relationship between samples and populations. If this part is known, in other words, if we know our population, we can determine the likelihood of getting a sample from it, which obviously would be unknown if it's a random sample. We dive into the population, we select one at random. We don't know what we're going to get, but we can determine the likelihood of getting a sample using laws of probability. But in statistics, we spend most of our time looking at the other direction, where the sample is known, but the population from which it came is unknown. And we call this inferential statistics. So that's kind of where we're headed. This part, the central limit theorem applies, right? Because we know, just as an example, we know our population mean, we know our population standard deviation, we know whether or not our distribution is normally distributed. And if we know all this, sample size restrictions that we've talked about again previously, I'm not going to go into that again because I've already taught it to you. We can determine the likelihood of getting a particular sample from this population using central limit theorem and sampling distribution. So we switched that this time, right? We have our sample, and we examine the unknown parameter in a population. Now, a couple of things that we're going to learn to do. We're going to learn estimation and hypothesis testing. And let me pump the brakes a little bit and explain to you why I'm going into so much detail. This is the third time that I've redone the videos in Math 6610. And what I have found is when even for students who take 6610 and 6620, then maybe come into Math 5500, I noticed that they truly don't understand the relationship between the central limit theory, sampling distributions, and hypothesis testing. So this video, actually probably the next three videos, is going to seek to clear up some of that confusion. All right, so what happens? Well, we have an unknown mu. But let's just say for the sake of this this problem, that we have a known population standard deviation. So from everything we learned in the central limit theorem, we know that the distribution of sample means will be normally distributed, and the value smack dab in the center of that distribution will be the mean. We don't know where it is. We don't know where this distribution is centered, but we know in theory that that value right there will be the mean. And then we know that the spread, if you will, the variance will be defined as the as the standard error, which is just sigma over the square root of n. Now, we know that from that the middle 95% of this distribution falls from negative 1.9 standard errors below the mean to positive 1.96. I think I got the, well, anyway, falls from negative 1.96 standard errors below the mean, or 1.96 standard errors below the mean, to 1.96 standard errors above the mean. Now, we know this distribution is out there lurking somewhere, and again, what we're trying to estimate is mu. So what I want to do is give you a brief illustration on how a confidence interval is created from this. So what happens again? We go in and we take a sample. Now, where does this sample lie? Well, we don't know, but we know there's a 0.95 probability that it falls from negative 1.96 standard errors below the mean, or I'm sorry, 1.96 standard errors below the mean to 1.96 standard errors above the mean. So again, we close our eyes, we get a sample mean. Now, let's talk about that sample mean a little bit. First of all, I know that, let's just call this my first sample mean. I know there's nothing special or holy about that sample mean. It's one of infinitely many that I could have got at random. But what I know is if I took another sample mean, I would get something different. If I took another one, I'd get something different. If I get another one, there'd be something different. Okay, I won't do that very long. It'll be annoying. But what I know is I have this distribution of sample means right, that we talked about in previous videos. And I go in and select one of these at random, and let's just say I get that one right there. Again, I know that these things are going to vary, so I need to create variation around this. Because we know that from the sampling distribution. And what we do is we focus in usually on what's called a 95% confidence interval. And the 95% confidence interval will take the form of our estimate. In this case, think X bar. There's no more reasonable thing to collect to estimate an unknown population mean mu than a sample mean X bar. We're going to add and subtract this natural variation, and we're going to call this the margin of error. Now, the estimate, our margin of error will always be our critical value times the standard error. Our estimate will be X bar. Our critical value, now this is where we have to depend on prior work done by statisticians. And we know that the distribution that is appropriate for estimating a population mean mu with population standard deviation sigma given is the z distribution. So we'll call this our z critical. We know that our standard error is going to be sigma over the square root of n. Now, some of this stuff is just things that you have to tattoo to the brain, right? But again, what I want you to understand at this point, well, I want you to understand a lot of things at this point, but what I want you to understand mostly is we come in, we have infinitely many choices for this sample mean that we're going to choose, select at random to estimate the unknown population mean mu. We don't know what it is. We're choosing one of these at random to estimate that. Because we know these things vary, these sample means vary, there's nothing holy about the one we get, we have to add and subtract natural variation around that. The next thing we do is we select a level of confidence. How confident do we want to be that this confidence interval that we're getting ready to create contains the unknown value? So we proceed by taking the estimate plus or minus the margin of error, and the margin of error in this distribution is defined by your z critical plus or minus times your standard error. So your estimate plus or minus the z critical times your standard error. Now, what happens is we go back to the original distribution and we see that the z critical in other words, the two standard values that contain 95% of the distribution between it, and this is from the standard normal distribution where we have mean 0, standard deviation 1, is 1.96. Now, the way that we can determine that is just to pull up R, and we can look at the area. Let me get this over here. For example, we can tap into this area right here. Well, we got to think if there's 95% right there, then there's 5% missing. So it tells me that 2.5% must be there. So I need to find the value from this distribution that has 2.5% of the distribution to the left. So in this, I would just use Q norm. I need 0.025. The mean 0, standard deviation 1, and you can see rounded to the 100th place I get negative 1.96.